Hello, everybody. It is my pleasure to announce the talk by Professor Elias Kiritsis. He will tell us about revisiting Coleman-de Luccia transition in AdS regime using holography. In his slide, the title is a little bit different, but the subject is the same. Please, Elias, 1 hour.
Thank you very much. Can you see my transparencies?
Right now we see you.
You're seeing me. So for some reason then, because let me try to share screen. I tried to share screen again because I was disconnected, but now it tells me, no, it's okay. So let me reshare my screen.
Yes.
Can you see my transparencies now?
Yes, exactly.
Okay, let me put them full screen now.
If you want to put in the full screen.
Yes. All right. So good evening or good morning, everybody. The topics I would like to touch upon in my today's presentation has to do with the well-known Coleman-de Luccia non-perturbative transitions in gravitational theories, and how they connect with holography and quantum field theories of de Sitter. And by connecting all of this, I think we will learn some more things from what we knew until now. This is work that has been done in collaboration with Joel Ghosh, Francesco Nitti, and Lucas Witkowski in several previous papers. So let me start by remind you that quantum systems in general can have many types of ground states, and typically we think of them mostly in the context of quantum field theory as minima of an effective potential. And in general, transitions to lower minima proceed via tunneling effects. Coleman was the first to understand this, and that such transitions are mediated by instanton solutions, Euclidean solutions of the associated Euclidean theory. And these Euclidean instantons provide eventually boundary conditions for the subsequent Laurentian evolution. Now, in the absence of gravity, instanton solutions start in the false vacuum and end in the true vacuum. However, in the presence of gravity, this process is richer. It was first studied by Coleman and his student De Luccia in 1980, and the corresponding Euclidean solutions are known as Coleman-de Luccia instantons. In the presence of gravity, the absolute value of the ground state energy is important, as usually happens in gravity, and therefore it determines whether the space-time is de Sitter, Minkowski, or anti-de Sitter. Now, it turns out that decays to de Sitter or Minkowski time are qualitatively similar to what happens in the absence of gravity. However, decays in the AdS case are different for two reasons. One is that not all decays are allowed, and usually this comes with the statement that gravity sometimes stabilizes some unstable vacuum. And the second is that the end point of the decay is not a true vacuum, but an FRW universe that undergoes singular collapse. There are some folk beliefs in the field, and these concern Coleman-de Luccia decays, since the CDL paper that today has 2,000 citations. The first is that the workhorse that people used, in fact, to study these transitions is the thin wall approximation. And it is believed that the thin wall approximation, as Coleman initially stated, in the absence of gravity, is applicable generically once the vacua are near degenerate compared to the Planck scale. The second folk belief is that instanton solutions generically exist and non-true minima are generically unstable. Moreover, once AdS-CFT correspondence came into play, it is believed that the interpretation of these two statements now from the point of view of dual conformal field theories is that conformal field theories without relevant operators either on R4 or on the generalized cylinder, that is R cross S3, are generically non-perturbatively unstable. Moreover, later, a condition was derived in the thin wall approximation by Harlow, and if we parameterize the energy of the false vacuum and that of the true vacuum in terms of the associated AdS scales and the length scales, then we can, in the thin wall approximation, we can approximate the solution inside the bubble as the stable AdS, stable AdS, outside as the unstable AdS, and in between we have a thin brane with tension sigma, and then sigma must satisfy an inequality for the transition to proceed. However, we do not know how to connect this sigma, which is a phenomenological parameter, to the properties of the scalar potential, which is usually what defines our gravitational theory. Now, AdS to AdS Coleman-de Luccia decays have received attention in the recent past for two reasons. First of all, string theory is full of AdS vacua, and therefore the tunneling issue is relevant. And second, the AdS-CFT correspondence provides a dual view to such processes. So let me give you a preview of what I'm going to address in this talk. We will study Coleman-de Luccia processes, first of all, beyond the thin wall approximation, and we shall correct some of the beliefs I mentioned already. What we shall show is that the Coleman-de Luccia instantons are very rare. They don't exist generically. And when they exist, they have implications for the relevant holographic conformal field theories, either on S4 or on de Sitter space only. What we will find is that in order for the instantons to exist, the dual quantum field theory must have non-perturbative renormalization group flows that skip fixed points, something which is exotic, and I will explain what that means later on. We will give an algorithm to construct potentials that have instantons, starting from those that generate skipping renormalization group flows in the flat case, that is when the conformal field theories are in flat space. We have clarified the conditions for which the thin wall approximation exists, and these conditions are not only that the initial and final energy should be very close together, but also the potential should be essentially infinitely steep. And therefore, because of this, we will show that gravitational theories that are dual to quantum field theories via holography, they will have no thin wall instantons. Or you can put it the same statement in a different way, that thin wall instantons are in the swampland. We have also considered the Laurentian evolution, that is after the transition happens via the instanton, and we have shown generally that the general belief that there is a singularity in the future is always true. Moreover, this singularity is protected by a null horizon. However, one can show, and I will discuss this, that the existence of this horizon means that the singularity cannot affect the dual quantum field theory on de Sitter, except after infinite time. Now, if there is an instanton, then one can show, and I will describe this, that the conformal field theory on de Sitter has two ground states, a symmetry preserving one and a symmetry breaking one. And we have interpreted the instanton amplitude of Coleman-de Luccia as the probability to find the symmetry breaking state in the Hartle-Hawking vacuum of the CFT defined on de Sitter. So let me remind you some of the basic things before I go on about Coleman-de Luccia transitions. To compute the transition rate, the instanton rate, first of all, we must find a Coleman-de Luccia instanton solution in Euclidean signature. And typically, this means a solution that involves a metric. We are in a theory of gravity, and the values of some scalar fields. Now, this solution describes a Euclidean bubble, where the false vacuum is asymptotically far, and the true vacuum is inside the bubble. And then, if you find such a Euclidean solution, then you can write the rate of this transition as some amplitude that is usually computed from one loop determinants times the same classical instanton factor, which is e to the minus the instanton action for the particular solution, which of course one would have to renormalize. And after the transition happens, the subsequent evolution involves a real-time evolution of the bubble with initial conditions which are given by the Euclidean instanton solution. So what happens in the real-time evolution is that the bubble expands with the speed of light until it covers the whole space. And typically, one makes two hypotheses. The first is that the incident solution has maximal symmetry, and if the gravitational theory has d plus 1 dimensions, maximal symmetry means OD plus 1 invariance in the Euclidean case, which is translated into an ansatz for the metric which has some radial direction psi and slices that are d-dimensional spheres with some scale factor that depends only on psi, and the various scalar fields can depend only on psi, and psi being a radial coordinate goes from 0 to plus infinity. Moreover, this solution must be regular at the center and must approach the false vacuum as psi goes to plus infinity. Now, this can be proven rigorously that the dominant solution has the symmetry in the absence of gravity, but no proof exists so far in the presence of gravity. So this solution describes a bubble where inside you have the true vacuum and outside you have the false vacuum that goes off to infinity. And the second assumption, which is there, of course, in order to be able to do calculations, is the thin wall approximation, that you can approximate the solution with true vacuum inside, false vacuum outside, and an infinitesimally thin wall, which is separating the two. It was shown already by Coleman that in the absence of gravity, this approximation is good if the difference in energy of the true and the false vacuum is small compared to the height of the barrier. However, it's not clear when you are in AdS that this is applicable, and we shall see this in more detail. Now, I will be using a simple theory to study this, but what I will tell, this theory will contain gravity and a single scalar with a potential, but what I'm going to tell you generalize to the case where you have many other scalars. So, So let me start with a gravity theory and write how a generic potential will look like. So here is the potential as a function of my single scalar field. It has maxima, it has minima, etc., etc. That's a kind of a generic situation. The minima are possible, let's say, vacuum for the theory. This is a false vacuum because it's at a higher energy as a true vacuum. Both of them are perturbatively stable, but in general, one could tunnel from this one to this one, from B to D. And basically, if one is looking for an instant-on solution that will mediate such a tunneling, basically it's an OD plus 1 invariant ansatz that I wrote before. Here is the metric again with a single scalar now. And basically, at the center, psi equals 0, phi of 0 should be at the true vacuum. And at infinity, which means far away, phi should be at the false vacuum. That's how we defined, in fact, the instanton. Whereas the metric will become near AdS, both near one or the other, and we will have what we usually call an AdS to AdS transition. So if we can find such a solution, which is regular, then we're in business. We have a Coleman-de Luccia instanton. Let me now turn to holography. Now, holography, of course, is a correspondence between gravitational theories like the one I showed you before with dual quantum field theories. And for example, if I look at the same sort of potential as I looked before, then the interpretation of this potential or the points of the potential in the dual quantum field theory is that the maxima of the potential corresponds to UV fixed points and therefore to UV CFTs. So if phi is sitting here and goes nowhere, this would be a UV CFT, the same here. The minima correspond to infrared CFTs. So if phi is sitting here or phi is sitting here, that would be infrared CFTs. And then solutions which start at this maximum and go to this minimum could correspond to renormalization group flows, to QFTs, that is renormalization group flows where you have some UV CFT that eventually flows into an infrared CFT. Therefore, extrema are CFTs, and in fact, when one is sitting at any extremum, the metric would be AdS. So that's well known. Now, according to Wilson, of course, a QFT is a renormalization group flow between a UV and an IR CFT, and therefore a solution that goes from one to the other would look a little bit like this sketchy picture. That is, this is a radial direction, that's the holographic direction. This is where the boundary of the space is, and that's where your UV CFT is sitting. and then slowly the geometry and the scalar field change. The geometry here is not AdS, but eventually if one gets to the center of the space, the scalar is getting back to the point B, and space becomes again approximately AdS. So that's what's the gravitational picture of a Wilsonian renormalization group flow. So to describe such a flow, the metric ansatz in general we write is similar. That is, we have the radial coordinate that now is called the holographic coordinate. We have a scale factor that depends on u, and then we have slices. And on the slice, you can put several types of metrics that depend only on the slice coordinates. And essentially, in this ansatz, the boundary metric is essentially this Gij. And usually in these coordinates, the AdS boundary is at u equals minus infinity. So according to the holographic duality, if you find such a solution, this is dual to the ground state of a quantum field theory, which is defined on this metric Gij. For example, if you take Gij to be Minkowski, you are describing the dual to a QFT defined on flat metric. If you take Gij to be a sphere, then you are defining a quantum field theory on the sphere. And if you take the sphere and you analytically continue in the standard way, then the sphere becomes de Sitter space, and you are describing the holographic dual of a quantum field theory on de Sitter space. So let me go back now and look again at the potential landscape we were looking before. The vanilla type of flows that we have, gravitational flows we have in this case, is to go from a maximum to a nearby minimum. And this type of flows, that is from here to here, or from here to here, or from here to here, etc. These type of flows, if you look at them, what they correspond to in the language of the dual quantum field theory is you have a single coupling, that's your single scalar, and then that means that the coupling constant line is a line, and then you have a UV fixed point corresponding to this, then you have an IR fixed point corresponding to this, a UV fixed point corresponding to this, an IR fixed point corresponding to this, and the flows have the same sort of structure as we would have in one-dimensional flows in quantum field theory. So this is standard. So let me now, in view of this dictionary I made between gravity and holography, try to interpret the Coleman-de Luccia instant-on solution in terms of holography. So in the Coleman-de Luccia transition, I need a solution that starts at a minimum, not at a maximum, and ends at another minimum. Here, for example, it starts at B and ends at D. And therefore, the false vacuum here is associated with a CFT, which I will call CFTB. It's when phi is sitting here. And the true vacuum is associated with another CFT. I will call it CFTD, where phi is sitting here. And if I find such a solution, which is regular, then I have an instant-on, and its dual interpretation would be that this CFT is non-perturbatively unstable to this, to become the CFT D. So a CDL instant-on is a solution where the flow starts at a minimum and ends at a minimum. And in general, we have shown by studying the structure of general such scalar equations that regular flows which start at a minimum and end at a minimum do not exist in general. They exist only if you fine-tune the potentials. That's number one statement. And if you try now to write the OD plus one invariant instant-on ansatz, which is written here in terms of the sphere and phi as a function of u, then the instant-on is a solution where phi at u minus infinity is sitting, that is, this is near the boundary, is sitting at the false minimum, and phi at some finite point will come near the true minimum. Now, the reason that this is true and you can never arrive exactly at D is because you can prove, in general again, that when the slices have positive curvature, they're spheres like they're here, you can never reach D. You will reach somewhere nearby D, and how close you will reach depends on what is the curvature of your sphere. So the solution then, the incident solution is interpreted as follows from the point of view of the conformal field theory that is sitting at the false vacuum. It is the ground state of this conformal field theory in which scale symmetry is broken because the scalar runs, and the metric now is not exactly AdS. However, the scalar phi doesn't correspond to a coupling constant in the dual quantum field theory, because phi, because you are at a minimum, is an irrelevant operator of the quantum field theory at B, but what it turns on is a vacuum expectation value, and therefore you have symmetry breaking. So the instant-on solution in holography corresponds to a scalar wave turning on in this CFT, and because now a scalar wave turns on, scale invariance is broken, and there is a non-trivial flow in the CFT, and you flow towards the CFT D. Now, there are many examples even in quantum field theory where this can happen, and N=1 super QCD in the baryonic branch is an example of the theory where an irrelevant operator can obtain a wave and break spontaneously conformal invariance. But this is the generic interpretation in holography of a Coleman-de Luccia instant-on solution. Moreover, since the slices of the solution are spheres, the CFT at B, the unstable, let me call it the unstable CFT, is not defined on flat space, is defined on a sphere. So all of the above imply that if a regular instant-on solution exists a la Coleman-de Luccia, the dual CFT at point B defined on a sphere has two competing ground states. One is a conformally invariant ground state, which is dual to phi sitting exactly at phi B and the solution for the metric being AdS, and a conformally non-invariant ground state that's dual to the flowing solution, that is the one, the instant on now that goes from here to here, where the OD plus 1, 1 conformal symmetry is broken to OD plus 1. And this second solution, as I said, is the Coleman-de Luccia instant. Therefore, the conclusion of this discussion is that a necessary and sufficient condition for the existence of a Coleman-de Luccia instanton, which drives the tunneling between B and D, B and D, is that the CFT, the dual CFT at B on a sphere has a symmetry breaking ground state. Are there any questions so far? So let me quickly now draw the strategy of what is the rest I will do. So we have two distinct problems. One is our original problem, a gravitational theory in D plus 1 dimensions and several ground states, several minima of the potential, and instantons that can drive transition between them. That's the Coleman-de Luccia problem. And then problem B is a holographic QFT in D dimensions that is dual to the gravitational theory in D plus 1 dimensions. And in this problem, first of all, holography maps what happens to the QFT to what happens in the gravitational theory and vice versa. And second, very important, the QFT fixes the ambiguities that exist in the gravitational theory, like the boundary conditions, because now we know what are the precise boundary conditions that we need to define the gravitational path integral. So we will define the gravitational theory via holography. Then we shall find under what conditions the instant-on solutions exist. We will examine whether the thin wall approximation is valid in the string theory or holographic regime. We will show that the Coleman-de Luccia transitions have implication for CFTs only on the setter. And we shall analyze the physical implications of the subsequent Laurentian evolution and discuss to what extent the bulk singularity is observable from the boundary. And let me first come to the issue of thick walls and when this is a good approximation. To define a thick wall, I have to define first of all what is a thick wall. So I have to decide what is the center of wall, and there is a reasonable choice, although it's not unique, that I will define the center of a wall that I will call R bar to be basically the radial position defined via my scale factor here at some specific point U bar, where precisely phi takes the intermediate value between the false vacuum, the value where there is the false vacuum and the true vacuum. That's a reasonable choice. If you change it a little bit, it doesn't make a difference qualitatively. But then I have defined now where the wall starts and where the wall ends. And that's also a matter of choice. And this you can define by choosing a number between 0 and 1 gamma, and defining the beginning and the end of the wall to be, for example, the beginning to be a percentage gamma close to one fixed point and a percentage gamma on the other side to be close to the end, to the other fixed point. Now, gamma, you can choose it anywhere between 0 and 1. And as we will see, qualitatively, it doesn't make a difference for what you choose once you keep it fixed. In the practical numerical solutions I will show you later, for example, we chose gamma to be 0.12. So in this way, then we define the beginning and the end of the wall. And once we have defined that, we can define a parameter, which we will call the thickness parameter. Now, this parameter determines how thick or thin is the wall. It's the difference of the in and out radii divided by the center. And in fact, if eta goes to 0, the wall will become infinitely thin. And here, for example, you see two pictures which correspond to real flows. You start at the false vacuum and you flow near the true vacuum because, as I said, you can never reach exactly at the false vacuum if your slices are curved. So these are two different flows. And here there is a color code in which the false vacuum is blue, the true vacuum is brown, and the area which is white is basically what you could call the wall. And of course, this wall is thinner than this one. So let me now come to the connection with the skipping flows. By studying carefully the gravitational equations, we can prove the following statement. I will not prove it for you, but if somebody cares, I can discuss it at the end. What you can prove is the following, that in order for an OD plus 1 invariant instant-on solution to exist that describes tunneling from this minimum, the false minimum, to the true minimum, then what must exist is a holographic RG flow solution from this UV fixed point to this IR fixed point, and this flow is unusual. Why is it unusual? Because it doesn't end at the next minimum. It skips these two intermediate fixed points and goes directly to this one. Now, we call, of course, if you have flat slices, this will go and it will end exactly here. Now, we call these skipping flows, and these are exotic because from the point of view of the dual quantum field theory, this phenomenon cannot happen in usual perturbative QFTs, because if I project now the couplings again on the real line, as we do in quantum field theory, this is the original UV fixed point, the first infrared fixed point, this one, this is the next UV fixed point, this is the next IR fixed point, and this flow looks like you start here and you go through them somehow. You go like this and you get here. That cannot happen in perturbation theory. So this is unusual, and it exists because in holography, the equations are second order. It's it's unusual, it's non-standard, it's not generic. And we don't even know if it really happens in top-down theories, that is, ones that you get from string theory. So far, we don't have an example. It could or it could not, but it can happen in bottom-up potentials. So, yes.
Elias, there is some question here. Maybe it can be asked. You can unmute yourself.
Yes, please ask me now.
Yeah, question is, why do you think that there is, or consider only the case where you have this left upper maximum? It may not exist simply.
You mean this may not exist?
Yeah.
Well, if this if your theory has a single minimum or two minima and a maximum, obviously a skipping flow doesn't exist, and in that case you can prove that there is no instanton. You need to have a skipping flow.
No.
What?
That should be incorrect. If your curvature of your AdS is small, then you're basically, or the gravitational effects are weak, then you always tunnel.
You tunnel only if you have regimes in your theory. Maybe, Valerie, you should keep your question for a moment. when I will come eventually to these, you will need, in fact, to neglect gravity for what you're saying to happen. If you don't neglect
but
gravity,
there are physical situations where you can indeed neglect gravity, right?
Not in holography.
I don't care about holography. I'm caring about gravity. And
Yes, but here I'm discussing situations where gravity is dual to holographic theories.
Right. So suppose your AdS radius is very large, then you're effectively in Minkowski space.
It's very large compared to what?
Very large compared to all the scales in your scalar theory.
I mean, my theory, as I wrote it, the simplified theory, it has M Planck, which doesn't appear, of course, in the solutions, and AdS scale. So what is small compared to?
Oh, you have parameters in your potential.
Sure.
The masses of the scalar fields is very, very
That's
small.
right. The masses, yes, okay. So if you can make some of these parameters large, then we will come to the issue I will be describing in terms of thin walls.
Okay.
So maybe you should keep your question until then.
Okay.
There is one more question on the way at the moment. From
Yes.
Yeah, hi, Elias. It's related to Valerie's question, because whether gravity is strong or weak, the existence of the instantons should depend only on the potential between the true and the false vacuum.
That's true.
Then why does it matter the existence or non-existence of this other maximum?
You will see in a moment. In fact, generically, in a potential, such solutions don't exist. The reason is, the intuitive reason is very simple. In fact, in general, when you try to find a solution, you have two integration constants. And if you allow them to be free, generically, the solutions are singular. In fact, they run off to infinity. You have to tune one constant against the other to get a regular solution. Now, if you start from here, in fact, you can do this tuning, and that's how you find regular solutions that end up here. However, if you start at a minimum, already you have to tune one of your solutions because you are at a minimum in order for your solution to be regular. So you don't have any other constant to tune. Therefore, generically, for a generic potential, you don't expect a regular solution. You have to tune your potential to get a regular solution. That's the generic reason why this is the case. And in fact, what happens is that when you have this skipping flow, what happens at the same time is that there is a flow where the scalar starts from here on this direction, but does not end up here. It turns around and it comes here. And therefore, you have a class of flows that are like this, the green flows. You have a class of flows that are like this, and the boundary between these two flows is precisely the solution you're looking for.
Your arguments don't have a Minkowskian limit, right? In Minkowski space, you always have this solution, as Coleman have shown.
What? Coleman has not shown anything in the AdS case. He has shown, this is true, what you're saying is true if one of the final points is de Sitter or flat space. But it's not true if both of them are de Sitter.
I'm saying that your arguments should be valid also in the limit when your gravity is switched off and you are in Minkowski space. And I don't see how.
No, that's not true. That's what I'm trying to tell you. The AdS.
No, we're living in Minkowski space, aren't we? If we lived in AdS with huge radius, I would not care about the gravitational effects, right? When I'm considering vapor to liquid transition, I don't care about gravity.
I agree that in the absence of gravity, the transitions always exist. In the presence of gravity, as Coleman already had shown, some transitions don't exist, right? I mean, that already is in Coleman's paper.
That's when the gravity is strong, right? When gravity is strong,
and that's also what the condition that you get by the thin wall approximation is. Anyway, let's discuss this maybe at the end of the talk. Okay. So, so there is a connection, in fact, with these skipping flows and the fact that the flow that is the instanton solution one is looking for is precisely the boundary of these two flows. And this flow, by the way, is also exotic from the point of view of holography, because it's a flow where the coupling starts, let's say, going in one direction, and then it turns around towards the other direction. And if you try to project this into the real line, let's say, as you would do in quantum field theory, it would be like you're flowing in this direction, this turns around and goes here, which of course cannot happen. However, I should remind you that all of these holographic flows are for quantum field theories defined on a sphere, not in flat space. So the question is, how can we fine-tune potentials so they have such instanton solutions or flows, if you wish? And the strategy we have is that we can start with a potential which admits flat slice skipping RG flows, that is RG flows that skip with flat slices. And this is easy to do because you can reverse engineer it. And already, I think Valerie, from what I remember, and some of his students have done similar solutions. And then you take this potential and then you modify it in a specific way so that you can generate now potential that has spherical domain walls by adding a small correction which modifies it slightly. And the idea is that since Coleman, we know that the existence of these tunneling solutions, in Euclidean space, you can think of them as a particle moving in minus the potential. So this is minus the potential. This particle such friction, because you have gravity, and in particular in the AdS, friction has the same sign everywhere. And the existence of a flat wall means that you can find a solution that starts at this top and then stops exactly at this top. And then the idea is to shift a little bit the potential up in this direction, so that when you let it start a little bit below, and you have to choose where you let it go, it will stop exactly here. And the interpretation of the fact that you have to move it a little bit away is because now your slices have non-zero curvature. Let me show you a concrete example where one can implement this. So this is a sextic potential reversed engineered so that it has skipping flows. The important thing is what parameters does it depend upon. I put the false minimum at 0. The true minimum is a parameter. It's at phi t. And it has two more parameters. LF is the AdS scale at the false minimum. And delta is precisely controlling the quadratic piece of the potential, and holographically is associated with the dimension of the irrelevant operator that will be driving the flow. And because it's a minimum, delta is bigger than the dimension of your boundary. So to this, I will add now a small perturbation. V0 is the parameter that controls how big this is. This is sextic again, but it's engineered that near one minimum and near the other starts at cubic, so it doesn't modify the scaling dimensions of the appropriate perturbing operators. And I will choose d equal to 3. And I have to remember that in this context, the dual conformal field theory has two scales. One is the curvature space of the sphere that you're putting upon, and the other is the non-trivial vacuum expectation value of the operator that's dual to my scalar field phi. All physical quantities depend on a single dimensionless parameter, and this is the dimensionless curvature, which is curvature divided by the appropriate power of the expectation value. So what we do is we derive numerically the O4 instanton solutions for the various potentials varying their parameters. And for a given then instanton solution, we record the value of the endpoint where it stops. We extract the anomalous, the dimensionless curvature R, and then we compute the thinnest parameter eta. And then at the end, we calculate the instanton action B, which has the structure that it contains a sort of trivial factor whose combination is essentially what you could call the n square of the dual quantum field theory, is proportional to the Planck scale. It has the volume of the sphere, and it has an extra dimensionless factor that depend depends on the details of the solution and which can be precisely defined. So let me show you a few numbers in this example. So basically, we vary, so we keep delta to be large and fixed. Phi t is 1. The thinness of the wall in the flat case is about 0.2. And then we vary the perturbation and we see where it ends. This is very close to the true minimum. And then we vary it so that this moves away. As you do that, the dimensionless curvature is increased. The thickness of the wall is increased. And as expected already from the general intuition, the instanton action is decreased, and therefore the instanton becomes more and more relevant. So these are the general observations. In fact, these are generic. This you can show that it's true in generic examples. Now, to consider here the thin wall limit, first of all, one can prove that the thinness of the wall, once you have a spherical slice, is always bigger or equal to the thinness of the wall when you have a flat slice. Now, once you have this, then for the example that we had, the flat thinness you can compute analytically for the potential I showed you, and it depends upon a factor which is scheme dependent, gamma. That's what you use to define the what is the thickness of the wall, and the other parameters is delta, the perturbing dimension of the operator, and the ratio of the two AdS scales. Now, if you want to achieve eta going to 0, that's the thin wall limit, you have to make sure that eta flat also goes to 0, otherwise you cannot do it. Therefore, we can study when eta flat goes to 0. And from this formula, in fact, you can see that in order for eta flat to go to 0, delta has to go to infinity while keeping the ratio of the two AdS scales finite. And if you write this ratio in terms of 1 plus the other parameters of the potential, phi t and delta, since delta goes to infinity, phi t has to go to 0, and therefore the two endpoints have to go to 1 on top of the other, as was expected, but also importantly, the potential barrier in between has to go to infinity because the dimension of the irrelevant operator has to go to infinity. So this is what you find, and this is true for generic cases. Now, the question is, can you get this limit in general gravitational theories that are dual to quantum field theories? Now, we know already from studies of four-dimensional theories via the bootstrap that there is always an upper bound on the dimension of the least irrelevant operator. This upper bound depends on symmetry properties, etc., but it has always the structure that this upper bound is a number that is of order 1. And therefore, that means that there are no theories where the least irrelevant operator has very, very high dimension. And if you look now in multiscalar cases, the instanton solutions typically will extend mostly along the scalars, which have the lowest or the lowest irrelevant dimensions. And therefore, this argument is telling you that for generic theories, generic gravitational theories that are dual to quantum field theories, you do not expect to have them thin wall instantons. Let me now come to the Laurentian continuation. After the tunneling happens, the instanton provides initial conditions for the subsequent Laurentian evolution. You start with the instanton solution. It's written again here, but now I parameterize the sphere in terms of the angle, the azimuthal angle theta. And we obtain the Minkowski continuation by doing two analytic continuations. One gets the interior of the bubble and the other the exterior. The exterior is obtained by taking theta to be pi over 2 plus I chi, that's standard, and then the sphere becomes the Sitter space, and therefore this is a space which is sliced by slices of the Sitter. In this case, After this analytic continuation, the Euclidean equations remain as they are, and therefore the solution that one found, the instanton solution, can be directly analytically continued, and it describes, in fact, the Minkowski solution outside the bubble. So to go inside the bubble, you need another analytic continuation, which is also well known. Psi has to go to I tau, theta to I eta. The old scale factor complexified has to become the new scale factor. And now the metric looks like inside minus dt square scale factor. And these are now Euclidean AdS slices. And as it is well known, this is an FRW universe with hyperbolic slicing with scale factor A of t. In Euclidean signature, of course, phi has to become a function of t, but now the equations are different. Now you have to take v to minus v, and therefore you have your old solution doesn't work anymore. You have to resolve these equations with the initial initial conditions given by the instanton, which are better shown, in fact, in this diagram. So in this diagram, this is the radial direction, this is time, this is the Euclidean geometry, this is the boundary of the Euclidean geometry, this is the Minkowski patch, this is the boundary in the Minkowski patch, this is the outside of the bubble, this is the inside of the bubble, and in fact, the bubble wall is a horizon. So this solution can be directly giving this solution here, but if you want to find this solution, you need boundary conditions on this Cauchy surface, and these boundary conditions are given precisely by this solution, which is equivalent, in fact, to the instanton solution because it's obtained by it. So this is well known, and moreover, typically people expect that inside this piece, you will have eventually a singularity or a big crunch in your Laurentian metric. So the singularity was argued since the time of Coleman. Banks gave further plausibility argument about its existence. One can prove that generically a singularity exists, and this is based on a proof of what the scale factor does. And in fact, let me show you the behavior, which in fact is generic. In fact, here you can see what the scale factor does from the beginning, that is from the horizon, where it increases and then eventually it collapses. This is showing, in fact, what W, which is a dot, that is the first derivative of the scale factor, does. It starts close to the horizon like this. It goes near the true vacuum, but because there, in fact, the friction becomes anti-friction, basically it oscillates and eventually is kicked away to infinity. And this is, in fact, the singularity. And a similar behavior you can find, in fact, for phi dot. So this, in fact, is generic and not surprising. Now I would like to interpret this solution from the quantum field theory point of view, because, in fact, people have tried to do before, and because our interpretation and our conclusion is different. So what I argued so far is that the solution here in the green patch, which is the same as here, is basically, from the point of view of the quantum field theory, is a flow from the unstable CFT defined on the Sitter space and driven by the wave of an irrelevant operator. The question is, first of all, can this conformal field theory, which is living on this boundary, see inside the bubble, and in particular see the singularity? Of course, the horizon and the singularity would hit the boundary at infinite time. The question is, can you learn anything before that? At least in terms of the correlators you can compute in the quantum field theory, it doesn't seem possible that you can see inside, because usually to compute this in holography, you put boundary conditions on the horizon. And therefore, what is inside, you cannot see. There are subtle points, in fact, where correlators, which are not retarded correlators or advanced correlators, may be able to see through the singularity, like Whiteman correlators, but I don't know if these are measurable. And if somebody knows whether these are measurable, he should tell me, because this is an important question which will turn around what I think. So From these arguments, one can conclude that the dual quantum field theory is unaffected by the crunch that happens inside and can only learn about it only after infinite time at the boundary, at the future boundary of the Sitter space. Therefore, the boundary CFT is the false vacuum CFT at all times, and in principle, one doesn't see vacuum decay, at least in the way we think in terms of gravity. This conformal field theory, as I mentioned, has two ground states, C1 and C2. C1, in fact, is when phi is sitting at the false vacuum and the interior is AdS. And this ground state, as I mentioned, preserves the full conformal field theory of the CFT, which is OD(2). And the vacuum expectation value in this ground state of the scalar operator is 0. And the other ground state corresponds to the wave flow solution, which corresponds to the instanton. Phi is non-trivial. The metric is not being AdS. And in this case, the conformal symmetry is broken. And the vacuum expectation value in this state of the scalar operator is non-zero. However, one can calculate that both states give the same wave for the stress tensor. Now, to interpret this further, in fact, we know that the false vacuum CFT defined on the Sitter has a special state. And this is known as the Hartle-Hawking state or the no-boundary state. And this is defined by doing the gravitational path integral with AdS d+1 boundary conditions. And by doing the gravitational path integral, you'll describe a wave function that describes this Hartle-Hawking state. And in fact, this wave function is precisely given by the on-cell gravitational action that is a functional of the boundary data. And since the theory has two semi-classical ground states, that means that the Hartle-Hawking state contains some overlap with these states. And I should remind you that the Hartle-Hawking state for a QFT on the Sitter is the one usually associated to the Bunch-Davis vacuum. So, in fact, if you want to calculate the overlap between the symmetric vacuum, the symmetric ground state with the Hartle-Hawking state, that's the associated wave function with the appropriate boundary conditions. And this is given from a holographic definition by e to the minus the on-cell action at the associated data. The same is true for the symmetry breaking vacuum. You have to calculate the associated on-cell action. And then when you compute the ratio of these two amplitudes, then this is the difference of the two actions. And this is precisely the renormalized instanton action of Coleman. Therefore, the instanton probability is controlling how much of the broken vacuum is in the Hartle-Hawking state of the false CFT compared to the true vacuum. So, in a sense, of course, first it indicates that the symmetry breaking vacuum is exponentially suppressed. On the other hand, the true vacuum CFT is hidden behind the horizon. Everything I told you so far reflects CFTs defined on the Sitter space, or spheres in the Euclidean case. However, people are interested what happens to these CFTs when they're defined on flat space or on the generalized cylinder. And in fact, there are claims that these CFTs are also unstable. Now, the argument for this is that you can start for the solution that we have where the slices are spheres, where the asymptotic metric is a sphere, and make a bulk diffeomorphism, which is well known in AdS, which changes the asymptotic geometry from a sphere either to R4 or to the cylinder. Now, if you do this and then you map the instanton, of course, the instanton doesn't have maximal symmetry, but that's not a problem. And in fact, you can use them, in fact, to argue that such CFTs are also unstable, in fact, when they are on the generalized cylinder. Now, a special property of this map is that it maps the infinite future of the Sitter to a finite time on the generalized cylinder. And therefore, in these coordinates, the singularity hits the boundary at a finite point. And this seems to imply that the boundary CFT on these manifolds, in fact, is hit by a singularity at finite time and therefore is unstable at finite time. However, what I would like to argue now is that if you use this OD plus 1 symmetric instanton that we have and you map it using the coordinate transformation, this does not correspond to vacuum decay because it has a non-trivial source for the scalar field. In fact, it describes a driven decay because if you take carefully the limit using a cutoff and then removing a cutoff about what happens as in the Minkowski geometry now, you find that the source of the scalar field is 0 for all times, but becomes a delta function at the finite time at which the singularity hits the boundary. Therefore, holographically, this is a driven theory, and therefore, this is not vacuum decay. We claim, therefore, that this map does not tell us anything about the instability of the same CFT, but now defined either on the generalized cylinder or the Minkowski spacetime. So let me conclude. We have considered Coleman-de Luccia transition from AdS to AdS. We have used holography to constrain such transitions and interpret them from the point of view of the dual CFT. We have found that generically there are no instanton solutions, except if you tune the potential. We have found that in order for instantons to exist, the dual quantum field theory must have non-perturbative RG flows that skip fixed points. The dual CFT must be defined on the Euclidean sphere because that's a source, and this is part of the definition of the boundary conditions for the gravitational path integral. We have given an algorithm to construct potentials that have instantons, starting from those that generate skipped RG flows, and we have clarified the conditions for the thin wall approximation to exist. And in fact, what we have found is for gravitational theories that are dual to holographic quantum field theories, there are no thin wall instantons. Or equivalently, one can say that the thin wall instantons are in swampland. We have also considered the Laurentian evolution and shown generically that there is always a singularity in the future. Such a singularity is protected by a horizon, and therefore it cannot affect the dual QFT except at infinite time. The dual CFT is living on de Sitter space, and if there is an instanton, then the CFT on de Sitter has two ground states, a symmetry preserving one and a symmetry breaking one, and we have interpreted the instanton amplitude as the probability to find the symmetry breaking state inside the Hartle-Hawking vacuum of the CFT on de Sitter. It's not known whether, in the absence of OD symmetric instantons, one might have ones with less symmetry. This is an open question, and the implications of this analysis for inflationary models remains to be investigated. And with this, I would like to thank you for your patience.
Okay, so any questions?
I have a question. Hi Elias.
Hello.
I'm wondering about this last point. Speculatively, what would be the implications for inflation?
I don't know, and that's why I mentioned that this remains to be investigated. I don't know yet, but it's worth thinking a little bit whether this has any implications for inflation. So right now, I don't have a good answer to your question, but I think it's worth thinking a little bit about it. In any case, that's something I'm currently doing.
Okay.
More questions, please.
Can I ask one?
Yes, please.
Hi, Elias.
Hi, Jose. Sorry, this is Giuseppe. I'm sorry.
Yeah. I'm confused about your point that the thin brane is only in the swampland, because I thought that swampland is usually meant to be theories that are inconsistent when are coupled to gravity.
The swampland, for me, is theories that you cannot obtain as string theories, which eventually are dual to quantum field theories.
But it seems a bit different than the definition that I mean, whether the theory has a holographic
The
dual or
definition
not.
is different, but the essence is the same. We're talking about the same theories. We're talking about theories that are effective theories of string theories or M theories, right?
Okay, so it's not the dual theory that is in the swampland, it's the bulk theory.
The bulk theory, yes.
Bulk, okay.
Yes.
And another question is this conclusion about the absence of thin brane is the same if you take the thin brane to be not in the bulk, but ending on the boundary for a defect, say.
In that case, you cannot interpret it as an instanton, as a Coleman-de Luccia instanton. In principle, you can have such branes, but in fact, let me also add another qualifier. We know that in string theory, we have in the limit in which the coupling goes to zero, which is the limit in which we study string theory, we have thin branes, we have D branes, right? So in principle, you can use D branes, but these D branes cannot appear as effective limits of theories with only scalars. You have to add other fields, or you have to add them explicitly in your theory. Okay, but if you are in a theory of scalars only, then what I said is true.
I see, okay.
I mean, in string theory, you can in principle have solutions in which you have transitions using D branes. Of course, in general, your bulk solution could be weakly or strongly curved, but you can study it typically when it's weakly curved. And in that case, you can use D branes as thin walls.
But then you have to worry if you can ignore the back reaction.
Typically, you can ignore the back reaction only when you go to the G equals 0 limit. But that's usually the limit we're discussing in string theory.
Okay, thank you.
Okay, next questions from Jose.
Yes.
Please.
Yes, Elias, I wanted to ask a totally naive question because I'm totally an outsider to these holographic constructions. Then, to be able to construct this holographic interpretation, your Coleman-de Luccia has to tunnel close to the true vacuum, or this is not needed?
In principle, it's not needed because how close you go, it depends on how curved is your bubble. Now, in general, for these solutions, you cannot choose that. That is, the curvature is not a modulus. You cannot decide what's the size of your bubble. It's decided by your solutions, right? It's only for, if a bubble exists, it will exist typically for one size. And therefore, how close you are depends on what potential you use.
Right. And then your claim that these Coleman-de Luccia solutions are not generic, this holds for any kind of Coleman-de Luccia? This is what you're claiming?
This holds for a generic potential, yes.
This
and it has to do with the fact that you are needing already two fine-tunings. One is to get a regular solution, and another one because you start from a minimum.
This cannot be true, right? Because I can construct whole families of Coleman-de Luccia solutions just by you give me a solution that you have, and then I change just the.
It makes, first of all, let me remind you something. It makes a difference if you are in AdS, flat space, or DS.
Yeah, you give me
you have
one
to be in AdS.
You give me one in AdS, and then I rescale the whole potential, the scale of the field, and then I will generate. Just by doing that, I'm generating new solutions until gravity is.
Sorry, you rescale the field until what happens?
Until you find a domain wall, and then after that, then you won't be able to find any solution. But in this way, you are generating whole families of solutions. So I don't think
you will find solutions like this. If you want, we can describe it. You can describe it in detail, but I don't think you will find solutions by scaling.
I think you do, or just tuning the strength of
the
gravity.
problem is that you need the regular solutions.
The
generic solutions are irregular.
They
have singularities in the Euclidean domain.
I can give you examples, concrete examples of this, because
maybe you should give me something concrete
will.
in writing so we can discuss it in detail.
Even analytic ones that you can control completely.
Analytic ones, one can construct, in fact, if one tunes the potential.
With free, I mean analytic with free parameters, in which you can see how you approach the domain wall and everything.
Sure. If you tune your potential, that's how we construct them also. We have to tune the potential.
No,
but if you
potential, the potential is tuned for the domain wall, but then you can depart from it and then you find generic solutions.
You have to write me something and then we can discuss it. So I know exactly what you mean.
Okay. The next question from Valery Rubakov. Valery,
yes,
please.
Concerning your singularity in Minkowski domain in future, what is this singularity? What the scale factor does, and what the scalar field does?
The scalar field runs off to infinity. In fact, you can show that these types of singularities for regular potentials, the scalar field has to go to infinity always, and the scale factor blows up. Now, if you ask me with what powers it blows up, we haven't checked it, but in principle, that's something one can.
I ask another question. For this to happen, you need to violate the null energy condition, which doesn't happen in the scalar.
No, it doesn't, because for these equations, effectively V goes to minus V, and therefore this violates the.
No, wait a second. You are with a positive potential. Is your potential positive in Minkowskian domain?
In the Minkowskian domain, yes, but the equations for the analytic continuation have a negative potential.
No, wait a second. I define my theory in Minkowskian domain.
Then the potential is negative because I'm in the AdS regime.
It is negative, but it is bounded from below.
That's right.
So how does it violate the null energy condition?
No, I'm sorry. No, it's not bounded from below. In fact, most potentials, when you go to the boundaries of his space, usually go to minus infinity. That's what we know from supergravity and from string theory.
I'm sorry, you draw your potential in your one of your slides, in several of your slides. Is this the scalar potential?
The scalar potential is a potential that's always negative, and for large phi goes to minus infinity. That's what all potentials in supergravities where we have.
I'm sorry, I don't understand. It is not bounded from below.
No.
What is the meaning of this theory?
What do you mean? What's the meaning of this theory? That's n equal 4 supergravity, for example.
No, there is no ground state at all.
Sorry, what do you call a ground state in a gravitational theory?
Minimum energy.
There is no energy in a gravitational theory.
Okay, the scalar theory doesn't have any ground state.
If you decouple gravity, indeed, this is an unstable theory, but this is not a problem when you have gravity.
So, when you showed your potential in the beginning, was it a scalar potential or what it was?
I saw a piece of it. In general, the potentials, for example, I'll give you the example that I used for the numerics, because so it has a phi 6, right? If phi goes to infinity, this goes either to plus or minus infinity, depending on what you take, the coupling, right?
So you send your potential to minus infinity?
Yes, because that's typically what the potentials do in all top-down cases that we know.
Okay.
You see, this is both negative and this is both negative.
Okay, fine. Then
now
you can see the pathological theory and get pathological behavior. Very good.
You see, typically we thought this was pathological theory, but I'm not sure if it's a pathological theory. Moreover, the behavior we're getting is not pathological, right?
Yeah, you have a singularity, it's pathology.
You think that if the potential was going to positive values, you wouldn't?
Of course, yes. You will not violate the null energy condition this way.
But the null energy conditions are violated because the potential is negative. Otherwise, you're not in the AdS domain, right?
No, it doesn't. It's violated not because the potential is negative.
But why is it violated then? Sorry, what is negative?
P plus rho, pressure plus energy density. And that doesn't matter.
I don't think that this is violated here.
If it is not violated, then you don't have big rip singularity.
Why not?
Theorem.
Well, maybe you have to give me the details of that theorem, because that's not what we're finding, and that's not what other people claim.
Yeah, if you have.
But maybe you have a point. You have to tell me exactly what the theorem is.
The potential is not bounded from below, then you may have all kinds of singularities in your theory. If the potential is not bounded from below, is bounded from below, then you won't.
Give me, or I will contact you to give me details about the theorem, because I would like to understand what is the claim first, and then I may have a statement to make. But right now, I have to know exactly.
Let's talk privately on that.
Yeah,
this is
sure.
Straightforward consequence of Einstein's equation.
Okay. More questions, please?
Maybe I will ask a short question.
Okay, please.
Elias, thanks for your talk. I'm curious what will happen if you will have higher derivative gravity in your setup.
It depends on what higher derivatives you add. Obviously, we know that in terms of what happens with flows, higher derivatives do give changes. It's difficult, of course, to know what higher derivatives. Higher derivatives, most of the time, we put them by hand, and we treat them as, we stop the theory at 4 derivatives, then we solve. And sometimes one can get, unphysical behavior, and by unphysical, I mean something that wouldn't happen if one is having the full set of derivatives. For example, sometimes C theorems can be violated, etc. So I would expect that if you add a finite number of higher derivatives, in general, many things can happen, but I would not expect qualitative changes. Of course, there will be specific higher derivative theories that will make qualitative changes, but then I wouldn't know if these are in the swampland or not. I mean, there is no independent way of judging. So what can I say? We know already that for other issues, higher derivatives can make important changes.
From string theory, I would expect infinite towers of derivatives here or there.
Of course,
somehow.
Of course. But if you are working in a limit in which this is let's say, a semi-convergent series, or at least a series that you can truncate, it's okay. Now, stringy examples, I think the only thing where you take into account all of them, we have very, very few examples where one can do the calculation. N equal 4 in a few dimensions is the only case I know. So it's difficult to do. I mean, in most cases, we truncate, we use some reasonable assumptions to exclude some higher derivatives, and then we hope that we get some idea of what happens. But from experience with other cases, I would expect that depending on what higher derivative terms you're getting, you might change drastically some of these things. RG flows change, in fact.
Nice.
And also you can get spurious fixed points that are not driven only by the potential.
I see. Okay, thank you.
More questions, please?
I have a question in relation with what Alexei asked before. My question is related to the higher derivatives. I mean, it was studied by Hawking in one of the papers, trace anomaly driven inflation, where R square term is included, assuming this n equal to 1 conformal fields, and that there was a discussion about how inflation can be, initial conditions of inflation can be explained from quantum cosmology. Do you have any comment with respect to the paper?
Yeah, in fact, this was first done by Starobinsky. I think Hawking added to this precisely relating it to wave function of the universe and initial conditions, but this is a very well studied concept. Using the conformal anomaly is probably the easiest way of entering higher derivative terms, and this is a doable project. And it has been done for several things, and I'm sure there are things that haven't been done so far. There are several works over a period of whatever, 40 years since the first Starobinsky paper that this topic has been discussed. And in fact, there are quite a few works recently which try to study the stability beyond the original discussions.
Yeah, so in their paper of Hawking, there is some relation of AdS CFT and R-square inflation. So,
That's right.
And coming back to your point, why did you find it's difficult to say something about inflation?
I'm not finding difficult to say something about inflation. I have a paper on this, but it's not related to what I'm telling you here.
Okay,
and many other people have papers on this.
Okay.
So not to confuse issues. Of course, first of all, what Hawking does is not what we usually call now Starobinsky inflation, which is R-square inflation. The original Starobinsky inflation is conformal anomaly inflation, to which, if you want, you can add R-square. But then on the way, Starobinsky found that if you want to have inflation that agrees with what we expect on inflation, it's better to do it with R-square, because conformal anomaly inflation has some other problems, etc., including agreeing with data. So Starobinsky inflation today is not what Starobinsky wrote in the first paper, which is anomaly inflation.
Yeah, okay. Okay, thank you.
More questions, please? Okay, maybe I will ask some general questions. As I understand, you have, there is no black hole in your consideration. What happens if one of a solution contains black holes? So what do you think?
Okay, indeed, I have no black hole. If I want to put a black hole in the story, probably I would have to ask the question to what extent a CFT on finite temperature is unstable, right? Probably. I don't know. I mean, quick answer, I don't know. But I'm thinking now, motivated by your question. My first guess would be that I would have to start with a CFT at finite temperature and then try to ask, at least that's the question on the side of quantum field theory, and ask if it's stable. On the side of Coleman-de Luccia, I'm not sure. I'm not sure if one can ask the question. Maybe if Valerie is still here, maybe he knows better. I don't see how I can put a black hole in this transition story. No, it's not clear, in fact, in gravity, what that would mean.
I see. I saw one more question. Pavel Slepov, please ask your question.
Oh, thank you. I have a small question. Is it possible to consider by the same way the case of non-maximally symmetric instantons? This case of maximally symmetric, yes?
Right, indeed. Of course, as you can imagine, the reason that people so far looked at maximally symmetric is because this is easier. And in fact, even this easier case, if you try to really deal with the full scalar action, this is quite complicated. The non-maximally symmetric is more difficult. However, that doesn't mean that it doesn't work, especially in cases where there is no normal instanton. There might be an instanton with less symmetry. The point is, can you find it? In fact, the instanton that you obtain by doing this diffeomorphism I mentioned in order to change the boundary metric is, in fact, in the new metric, it is a non-maximally symmetric instantons. The only problem with it is that it induces a scalar source. Otherwise, it would have been okay. So there could be less symmetry instantons if there is no maximal symmetry instantons. The challenge is to find them. But of course, that doesn't mean that it's impossible. It's just harder.
Oh, okay, thank you.
Okay. More questions, please? Okay. If there is no questions, let's thank Elias for his very interesting talk. As I understand, there are many questions. There are, I think maybe next time we can see more progress and maybe ask more questions. Okay, thank you
very much for the invitation. And thank you, all of you, for your patience.
Yes, thank you. Thank you.